Our last review topic, woohoo! Modern quantum physics. Modern/quantum. So, here's the thing. We normally think of light, I bet you do, as a wave. But light can be thought of as actually little packets or particles of light called photons. Those little photons have some energy, of course. They come in and they can move something like electrons. That's what solar cells do. The light comes in and moves the electrons. They transfer momentum and energy. Even though light doesn't have mass, it has momentum because it moves electrons. So it moves those electrons, and energy and momentum are both conserved. Remember those things? And also we can figure out the energy of this little, now I like to do it, I'm going to make it a little bit bigger actually. So if we have, light, you can think of it like a wave going in a particle almost. Like if this is your light source over here, say this is your laser, then your laser right here, plugged in, maybe we should give it a little red, okay? That laser will have photons of light where they have energy and momentum. You can figure out the energy by E equals hf. Remember Planck's constant is 6.63 10 to the minus 34 joules times seconds.
Rebecca Hoffman and Brian Frisbee-Geis. Rebecca Hoffman and Brian Frisbee-Geis, please.
Thank you for that announcement. During the video. Now, this graph, what's it going to look like? Yes, it's going to look like that because they're directly related, no squared. The slope is E over F, which equals H. Slope is Planck's constant. So every single graph you did would have the same slope there. E equals hc over wavelength would be energy of a photon versus wavelength. What would that be? They're indirectly related, would be like that. They wouldn't ask you about the slope because it's changing. The slope is changing. Photons have momentum and energy, and the momentum and energy are both conserved. Remember, you have these spectral lines caused by electrons going from one energy level to another. For hydrogen and mercury, you need to know. High to low is emission. It gives off light. Low to high on the levels is absorption. And you find out the energy by taking the difference in the two levels in evolts. How do you convert evolts into joules? Every single evolt is equal to, evolts like an inch or a centimeter, every single evolt is equal to a small number of joules. Okay? 1 evolt is equal to that many joules. So you can set up a proportion between there. Remember, evolt numbers are typically between 1 and 10 or 1 and 20, you could say. And you can remember that by looking on your reference tables right here. Those numbers in evolts are typically, less than 20, but in the whole numbers. And then joule numbers are like 10 to the minus 19. Frequencies are 10 to the 14th, usually. And wavelengths are usually 10 to the minus 7 if we're talking visible light. And also a couple more things. E equals mc squared. The graphs. E versus m. Good. And E versus C. You know that one? Vega? Vega? Yeah, buddy. Not squared, directly related. Squared, but still directly related with the squared. If you use this right here, if you plug in mass in kilograms, you're going to get energy in joules. If you want to do it in atomic mass units, you get MeVs. That's another relationship. That one you do not have to plug in there. It's its own relationship. You would set up a proportion based on how many U's you have. Each U is about the mass of a proton or a neutron. The actual masses in kilograms for protons, neutrons, and electrons are on the front of the reference tables. And last thing is about quarks, baryons, mesons, all that kind of good stuff. If I ask you, say somebody was walking down the street and another person asked them, hey, what's the quark content of a proton? First of all, I would wonder what community they're in, because this is apparently a pretty intelligent community, or a weird one. But if you step in a pile of protons, you're stepping in a pile of dew. Remember that? It's down, up, up. How about neutrons? Neutrons are neutral. They're duds. These both are baryons because they have 3, count them 3, 1, 2, 3, quarks. Not 3 different quarks, but 3 quarks. And if you look on your reference tables, Where is it? Oh, it was right on the page I was on. Anyway, baryons, right here. Baryons are 3 quarks. A meson is a quark and an antiquark. So they are giving you that type of thing. So for instance, if I have up anti-strange, that would be a meson, and the up would have a charge of plus 2/3 E. And by the way, the E is 1.6 10 to the minus 19 coulombs on the front of the reference tables. The letters, the symbols are in the middle, remember? And then your anti-strange, well, strange is negative 1/3, so anti-strange is positive 1/3. So apparently this would be a plus 1 E, same charge as the charge in a proton. Is it a proton? No, 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 no. This is a proton. We were just talking about that. But it's the same charge as a proton. It's been a pleasure reviewing with you. Thank you very much. And do well on the Regents 5 practice exams and lots of prayer. Thank you.